Greetings to everyone. My name is Guganesswari Nagendrian. Today I will present our proposed project entitled A Proposed Framework for a Portable Real-Time ECG-Based Arrhythmia Detection and Classification System using Machine Learning on an Embedded ESP32 platform. This project focuses on the development of a portable ECG monitoring system that can detect and classify ECG signals into normal and abnormal categories using machine learning. Our group members are Guganesswari Nagendrian, Safia binti Azmi and Siti Sabaria binti Salihin. Together, we are proposing a portable intelligent ECG-based system for arrhythmia detection and classification using machine learning. This project proposes a portable, low-cost and intelligent ECG monitoring system called PREDACE ML. Cardiovascular disease is one of the leading causes of death worldwide, and arrhythmia is one of the major heart disorders that can cause serious complications if it is not detected earlier. ECG monitoring is important because it helps to observe the electrical activity of the heart and detect abnormal cardiac signals. However, conventional ECG missions are usually bulky, expensive, and mostly limited to hospital environments. Because of this, they are less suitable for continuous monitoring at home and in remote areas. Therefore, this project proposes a portable real-time ECG-based arrhythmia detection and classification system using machine learning on an ESP32 platform. The system integrates an AD8232 ECG sensor, ESP32 microcontroller, and a web-based ECG monitoring dashboard for a real-time ECG signal acquisition, visualization, and remote monitoring. For the machine learning part, ECG data from the MIT BIH arrhythmia database will be used to train and compare several models including logistic regression, linear SVM, KNN, and random forest. The best performing model is expected to be selected for real-time ECG classification. The ECG signal will be also processed using filtering to reduce noise and improve signal quality before classification. In addition, a PostgreSQL database will be used to store ECG data for long-term monitoring and analysis. The expected outcome for this project is a portable, low-cost and intelligent ECG monitoring system that can classify ECG signals into normal and abnormal categories while supporting continuous and accessible heart monitoring outside clinical environments. This slide shows the general ECG procedure and examples of normal and abnormal ECG signal patterns. An electrocardiogram or ECG records the electrical activity of the heart using electrodes placed on the patient's body. A normal ECG waveform usually has a regular rhythm with clear P wave, QRS complex, and T wave patterns. Meanwhile, abnormal ECG patterns may show irregular rhythm, QRS widening, ST depression, or ST elevation. These abnormalities can indicate possible cardiac problems and may require earlier detection and monitoring. An electrocardiogram or ECG is the primary diagnostic tool used to monitor heart activity and detect abnormalities in cardiac electrical signals. Arrhythmia refers to an abnormal heart rhythm caused by disturbance in heart's electrical conduction system. It can be identified through abnormalities in ECG signals. However, conventional clinical-grade ECG systems are often bulky, expensive, and require hospital-based operation. This makes them unsuitable for continuous real-time monitoring in home or remote environments. Therefore, this project proposes a portable intelligent ECG system using an ESP32 microcontroller, AD8232 ECG sensor, OLED display, and machine learning classification. The machine learning models including KNN, logistic regression, random forest, and linear SVM will be compared. The best performing model is expected to be selected for normal and abnormal ECG classification. For this project, the standard referred to is NC AMI EC57. This standard groups ECG heartbeat annotations into several categories including normal beats, supraventricular beats, ventricular beats, fusion beats, and unclassifiable beats. In this project, the ECG categories are simplified into two main classes which are normal and abnormal. This simplified classification is more suitable for a portable and hardware-friendly embedded ECG monitoring system. This slide shows the first part of the literature review. Previous study shows that deep learning and machine learning methods can improve automated ECG arrhythmia classification. Some studies also applied the AAMI EC57 category mapping to classify heartbeat types using the MIT BIH arrhythmia database. Random forest also be reported as a useful model for the ECG feature selection and heartbeat classification. However, several studies require large dataset, high computational resources, or mainly dataset based without complete hardware implementation. This supports the need for a more portable, low-cost and embedded ECG classification system. This slide continues the literature review. Several studies are focused on portable ECG monitoring system using embedded hardware, remote communication and IoT-based monitoring. This study shows that portable ECG system can support remote observation and preliminary diagnosis. Other studies focused on ECG artifact removal because ECG signals can be affected by motion artifact, noise and interference. However, many systems focused only on signal execution, artifact removal or IoT monitoring. They do not fully combine ECG execution, machine learning and classification database storage and dashboard monitoring in one portable system. This slide presents more studies related to ECG execution and machine learning classification. The AD8232 ECG sensor has been used in previous real-time ECG applications showing that it can acquire ECG signals for machine learning evaluation. Machine learning methods such as KNN, SVM, logistic regression, and random forest have also been applied for ECG arrhythmia classification. However, some studies are limited to specific arrhythmia classes, while others use deep learning models that require higher computational power. Because of this, deep learning may not be suitable for low-cost embedded systems with limited processing resources. This slide shows the final part of the literature review. Several studies support the use of ECG features such as pre-RR interval, post-RR interval, R-peak and QRS interval for heartbeat classification. Random forest also shown a strong performance in ECG beat classification because it can handle feature-based data effectively. Based on these findings, this project uses selected ECG parameters and a random forest model. This approach is selected because it is more suitable for a hardware-friendly, low-cost and portable ECG monitoring system. From the literature review, several limitations and research gaps were identified. First, many previous studies are software-focused and have limited emphasis on complete real-time hardware implementation. Second, some studies use too many ECG features or advanced feature extraction methods which can increase processing complexity. Third, full integration between ECG sensor, machine learning and database and dashboard in one portable system is still challenging. Fourth, some high accuracy ECG classification methods require high computational resources, making them less suitable for low-cost embedded hardware. Lastly, many portable ECG systems mainly focus on signal execution, display, or heart rate monitoring, but not intelligent real-time arrhythmia classification. Therefore, this project focuses on hardware-friendly portable ECG system using selected ECG parameters and random forest for real-time ECG, real-time classification and monitoring. Cardiovascular disease remain a major health concern worldwide, and arrhythmias require early detection to prevent severe complications. Although ECG is the main tool for diagnosing cardiac abnormalities, conventional ECG systems are usually expensive, bulky, and limited to clinical environments. Existing portable ECG devices are more accessible, but many of them are limited to the basic heart rate measurement. They do not integrate machine learning-based classification for real-time detection and normal abnormal ECG patterns. Another problem is that raw ECG signals are highly affected by noise, motion artifacts, and environmental interference. These disturbances can reduce signal quality and affect classification accuracy. In addition, implementing machine learning into low-cost embedded systems is challenging because a limited memory, processing power, and computational resources. Therefore, there is a need for a portable, low-cost, and intelligent ECG monitoring system that can perform ECG execution, signal processing, arrhythmia classification, and data storage. This slide summarizes the main problems of novelty of the project. The first problem is that current ECG systems are bulky, expensive, and mostly limited to clinical environments. The second problem is that existing portable devices lack intelligent arrhythmia classification capabilities. The third problem is that ECG signals are highly affected by noise and motion artifacts, which can reduce the accuracy. The fourth problem is that real implementation of machine learning on low-cost embedded system is challenging. The fifth problem is that there is no fully integrated solution combining execution, processing, classification, and data management in one portable system. The novelty of this project is that it integrates ECG signal execution, AD8232 signal conditioning, ESP32 processing, machine learning, classification, and database storage in one portable system for real-time arrhythmia detection. Objectives of this project are: the first objective is to develop a random forest-based machine learning model for accurate arrhythmia classification using the MIT BIH arrhythmia dataset. The second objective is to integrate the trained random forest model into the ESP32-based system for real-time ECG signal classification. The third objective is to design a portable ECG monitoring system using AD8232 ECG sensor, ESP32 microcontroller, and a web-based ECG dashboard for real-time signal execution and classification. The fourth objective is to evaluate the performance of the proposed system and store ECG data using a PostgreSQL database. The scope of this project focuses on developing a portable ECG monitoring system using ESP32 and AD8232 ECG sensor. The system is designed for real-time signal execution, pre-processing, and arrhythmia classification using hardware-friendly machine learning models. The system is designed for real-time execution, pre-processing, arrhythmia classification, and using hardware-friendly machine learning models. The system also includes lightweight signal processing, OLED-based visualization, PostgreSQL-based data storage, and web dashboard monitoring. The classification is limited to normal and abnormal ECG patterns based on selected AAMI EC57 categories. System performance will be evaluated using accuracy, sensitivity, and specificity based on the MIT BIH arrhythmia database, validation, and real-time testing. This project does not cover full clinical diagnosis, multi-lead ECG analysis, or advanced deep learning models. It is limited to single-lead ECG execution using 3 electrodes and simplified processing suitable for low-cost embedded hardware. This project has 4 main significances. First is it supports early monitoring by detecting abnormal ECG patterns before serious complications occur. Second, it provides a compact, portable, and low-cost ECG monitoring solution suitable for non-clinical and resource-limited settings. Third is applies machine learning to classify ECG patterns as normal or abnormal. Fourth is to store the ECG result in PostgreSQL, allowing monitoring history to be recorded and reviewed for the future analysis. Overall, this project is expected to improve accessibility to heart monitoring by combining ECG execution, machine learning classification, and database storage in one portable system. The methodology consists of dataset preparation, ECG feature selection, machine learning model training, and comparison, followed by portable ECG system development using ESP32 and AD8232. 4 ECG parameters are used for the hardware-friendly model. These parameters are pre-RR interval, post-RR interval, RPIC, and QRS interval. Several machine learning models are trained and compared, including Canaan logistic regression, linear SVM, and random forest. Random forest is selected as the final model because it is suitable for the selected ECG features and more practical for low-cost embedded implementation. The system is expected to display results through the OLED display and web dashboard. The prediction data will also be stored in the PostgreSQL for the monitoring purposes. The performance of the system will be evaluated using accuracy, sensitivity, and specificity. These slides explain the integration between machine learning and PostgreSQL. For the machine learning part, SVM, Canaan, logistic regression, and random forest models will be trained using the MIT BIH arrhythmia database. The best performing model is expected to classify ECG signals into normal and abnormal categories. For the database part, PostgreSQL will be used to store and manage ECG data, pre-processing outputs, and machine learning results. PostgreSQL is expected to act as a bridge between the hardware data collection stage and the software-based machine learning pre-processing stage. This integration supports real-time monitoring, data storage, and future analysis of the ECG results. This slide shows a proposed system architecture. The system begins with machine learning preparation using ECG data from the dataset. The selected ECG features are used to train and compare the several models. After models training and evaluation, the best performing model, which is expected to be random forest, will be selected and deployed. On the hardware side, the AD8232 ECG sensor acquires the raw ECG signal from the user. The SP32 microcontroller read and process the ECG data. The processed ECG data is then sent for classification. The output result will classify the ECG signal as normal or abnormal. The result can be displayed through the OLED display and the web dashboard, while the ECG data and prediction result can be stored in the PostgreSQL database for the monitoring and analysis. This slide shows the four ECG parameters used as input features for the random forest model. The first parameter is the pre-RR interval. It is time interval between the previous R peak and the current R peak. It is used to analyze the heartbeat rhythm variation. The second parameter is the post-RR interval. It is time interval between the current R peak and the next R peak. It helps to detect the irregular heartbeat timing. The third parameter is the R peak. It is highest peak in the QRS complex and it is used as the main reference point for the heartbeat detection. The fourth parameter is the QRS interval. It represents the duration of the QRS complex and supports abnormal ECG classification. These four parameters are selected because they are meaningful ECG features and suitable for the hardware-friendly random forest model. This slide explains the flow of dataset loading, model training preparation, and output file generation. First, the Python project folder is open. The folder contains the source code, dataset files, and output files. Next, the ECG dataset CSV file from the MIT BIH Arrhythmia database is loaded. Then, the Python training script is executed, and the required libraries such as pandas, numpy, scikit-learn, and joblib are imported. After that, the dataset is read into the Python for pre-processing. The dataset summary is checked, including the shape, columns, missing values, and label distribution and data types. The dataset is then cleaned by removing the unnecessary or incomplete columns. Next, the important ECG features columns are selected, such as pre-RR interval, post-RR interval, R peak, and QRS interval. The target label is set as binary class, which normal is labeled as 0 and abnormal is labeled as 1. After that, the input and output data are prepared. The selected ECG features are used as the input and the binary classes is used as output label. The dataset is then split into training and testing sets. Several models are trained and compared, including KNN, logistic regression, random forest, and linear SVM. Finally, the output files are saved. These include Python files, cleaned CSV files, selected features files, JSON files, joblib model files, training report files, and deployment files. The best performing hardware-friendly model will be selected for integration with the ECG monitoring system. This slide shows the hardware components used in the proposed ECG system. The first component is the ESP32 microcontroller. It acts as the main controller of the system. It processes the ECG data and sends results to the backend through Wi-Fi. The second component is the AD8232 ECG sensor. It acquires the ECG signal from the user and filters or conditions the signal for monitoring. The third component is the ECG electrodes. These electrodes are attached to the body to detect the electrical activity of the heart and provide the input signal to the AD8232 sensor. The fourth component is the OLED display. It displays the ECG classification output and shows whether the result is normal or abnormal in real time. The fifth component is the power supply or power bank. It provides the portable power to the system and supports real-time operation outside clinical settings. The sixth component is the jumper wire and breadboard. These are used to connect the hardware components during the circuit development. The hardware workflow starts from the ECG electrodes, then to the AD8232 ECG sensor, followed by the ESP32 microcontroller, and finally to the OLED display or backend system. This slide shows the flowchart of the proposed ECG signal acquisition and machine learning based classification system. The process starts by powering on the ESP32 system. Next, the AD8232 ECG sensor, OLED display and Wi-Fi connection are initialized. After that, the ECG electrodes are attached to the body. The ECG signal is then acquired from the AD8232 ECG sensor. The ESP32 processes the ECG signal and extracts the required ECG parameters. The extracted parameters included pre-RR interval, post-RR interval, and R-peak and QRS interval. These parameters are then sent to the trained machine learning model. The machine learning model classifies the ECG signal. Finally, the result is displayed on the OLED display or dashboard as weighting, normal or abnormal. This slide lists the biomedical sensor and hardware components proposed for the ECG system. The first component is the ECG electrodes. The ECG electrodes act as the input transducer. Their function is to detect the electrical activity from the body surface. The second component is the AD8232 ECG sensor. It is a biomedical biopotential sensor. Its function is to amplify and filter the weak ECG signal. The third component is the ESP32. It acts as the microcontroller that reads and processes the analog ECG signal. The fourth component is the OLED display. It acts as the output device to display the ECG classification result. Together, these components form the complete ECG sensing, signal conditioning, processing, and output display. This slide explains the AD8232 ECG sensor overview. The AD8232 ECG sensor module is proposed as the main biomedical sensor in this project. The sensor type is the biomedical biopotential sensor and ECG analog front end. The input of the sensor comes from RA, LA, and RL electrodes. The output is an analog ECG voltage signal that is sent to the ESP32 ADC. The signal unit can be represented in millivolts or as an analog ADC value after the ESP32 reading. The main function of the AD8232 is to amplify and filter weak ECG signal for arrhythmia monitoring. In simple terms, the ECG electrodes detect the heart's electrical activity. The AD8232 conditions the signal and the ESP32 processes the signal for the future extraction and classification. This slide shows the AD8232 ECG signal conditioning circuit. The AD8232 amplifies weak ECG signals using its analog front-end circuit. This is important because ECG signals from the human body are very weak and cannot be processed directly without conditioning. The high-pass filtering stage helps to remove baseline wonder and electrode offset. The low-pass filtering stage helps to reduce high-frequency noise. The right leg drive or RLD improves common mode noise rejection and helps to produce a more stable ECG signal. After amplification and filtering, the conditioned analog ECG signal is sent to the ESP32 ADC for processing. The key function of this circuit are amplification, filtering, noise rejection, and analog output to the ADC. This slide shows the proposed schematic diagram of the ECG system. The schematic includes the connection between the AD8232 ECG sensor, ESP32 microcontroller, and the OLED display. The ECG electrodes are connected to the AD8232 sensor through the RA, LA, and RL inputs. The output signal from the AD8232 is connected to the ESP32 for signal reading and processing. The OLED display is connected to the ESP32 to show the ECG result. This schematic is important because it shows the hardware integration between ECG signal acquisition, microcontroller processing, and output display. This slide explains the function of ECG electrodes as the input transducer. The ECG electrodes are placed on the body surface to detect the electrical activity of the heart. They act as the input transducer because they convert the ionic current from the skin into an electrical signal. This project uses 3 electrodes in the single lead ECG system. RA means right arm, LA means left arm, and RL means the right leg. Proper electrode placement is important because it helps to reduce noise, improve skin contact, and provides a stable ECG signal for the AD8232 sensor. The signal flow starts from the heart electrical activity, then to the ECG electrode, followed by the AD8232 sensor, and finally to the ESP32. This slide explains the signal conditioning process of the ECG signal. First, the raw ECG signal is received from the body. The signal is very weak and easily affected by noise. Second, the signal goes through amplification, where the AD8232 strengthens the weak ECG signal. Third, filtering is applied to reduce unwanted interference and noise. Fourth, a cleaner ECG signal is produced. Finally, the conditioned analog ECG signal is sent to the ESP32 for processing. This signal conditioning stage is important because better signal quality can improve the reliability of ECG feature extraction and machine learning classification. This slide shows the flowchart of the proposed ECG arrhythmia detection and monitoring system. The process starts with the initialization of the ESP32 AD8232 sensor, Wi-Fi and backend API settings. Then, the system reads the ECG signal or ECG parameters from the sensor system. Next, the 4 ECG parameters are prepared. These parameters are pre-RR interval, post-RR interval, R-peak and QRS interval. The system then checks whether the parameters are valid. If the parameters are not valid, the system repeats the ECG reading process. If the parameters are valid, the ECG parameters are sent to the backend server. The saved random forest model in job-lib format is loaded. The machine learning model is predict the ECG class as either normal or abnormal. After prediction, the ECG parameters and prediction results are saved into the PostgreSQL database. The result is then displayed on the serial monitor or dashboard. If monitoring continues, the system repeats the process. If monitoring stops, the process ends. The expected outcome of this project is the development of a portable and low-cost ECG monitoring system. The system is expected to perform real-time arrhythmia detection using a random forest-based machine learning model. It also expected to provide instant feedback through the OLED display, and also web-based dashboard. In addition, the system is expected to demonstrate the feasibility of integrating machine learning, embedded system, and database storage for real-time healthcare monitoring in non-clinical environments. The impact of this project is to support early detection of abnormal ECG patterns. It also improves accessibility to heart health monitoring, especially for remote and resources-limited areas. Overall, this project enables real-time, low-cost and portable arrhythmia detection for continuous heart monitoring outside clinical settings. In conclusion, this project aims to develop PREDACE ML, a portable ECG monitoring system capable of real-time arrhythmia detection and classification. The proposed system uses the ESP32 microcontroller, AD8232 ECG sensor, selected ECG parameters, and a random forest-based machine learning model. The system is expected to classify the ECG signals into normal and abnormal categories. It is also supports the accessible heart monitoring through OLED display output, web dashboard monitoring, and Postgres data storage. Although this system is not intended to replace clinical ECG machines or professional diagnosis, it can support earlier monitoring and improve accessibility to heart health screening outside the clinical environments. These are the references that we used in this project, and this is the second part that we used in our project, the references. And lastly, thank you. This is our presentation. Thank you for watching and listening to our proposed project presentation on PREDACE ML, a portable real-time ECG-based arrhythmia detection and classification system using machine learning on an embedded ESP32 platform. Thank you.